exclusive ORs and exclusive NOR gates, which is kind of a misnomenclature, and we'll talk about that in a minute. So exclusive ORs and exclusive NOR gates, these are combinational logic circuits. And what's the combinational logic circuit? What is combinational logic? Two or more, multiple, combining basic gates to perform a more complex function. These guys are used so often that they have a unique symbol. So we know the symbols for the basic gates. And most combinational logic circuits, by the way, they use the world famous triangle. They use the world famous rectangle. So we're going to see this symbol a lot. And the way you identify most combinational logic is the name of the pins. The exclusive OR gate and exclusive NOR gates are used so often they have their own unique symbol. They're called gates, but they're combinational logic. They're made out of more than one gate. We use these as digital comparators. We use them as parity generators, and we use them to do math. They actually can do addition with binary addition. So I guess I should put binary adders. So here's some circuits. They're made out of just standard basic gates. So let's do the truth table on A. And they're calling the output W. How many combinations can I put on these inputs? How many binary combinations can I put on that input? Yeah, two inputs. 2 squared would be 4, right? Yeah. Okay, so let's put the first one on there. 0, 0. Now what would we get out of this one? Okay, it says it takes all highs to get a high, right? I'm sorry, it takes all highs to get a what? Low. No way I can have all highs, right? What would we get out of this one? Any high, 0, good. What would we get right here? Huh? Takes all highs to get a low. Do I have all highs? So what do we have? Oops, sorry. Okay, so what do we have right here? Guys, this guy right here says it takes all highs equals a low. There's no way in the world. As soon as I got that 0 on that one input, I realized that the output cannot be low. It's got to be what? Now, what does this guy right here says? It says any high to get a high. Do I have any high? Okay, so what would this output do? It goes 0, right? Okay. So our next combination would be this guy right here, right? So what would I have right here? Good. What would I have right here? Okay, what would I have right here? 0, right? You follow me so far? And then our last combination would be this. So what would I have right here? What would I have right here? What would I have right here? So what can I tell with this circuit? Well, look at these guys right here. What's unique about these two outputs right there? Yeah, well, we don't use all lows or all highs here, but if they're the same, if the two inputs are the same, I get a 1 out. If they're different, I get a 0 out. So I can look at this output and I can tell right off the bat if the two inputs are the same or if they're what? Different. So I'm comparing those two inputs. But I don't have to even know what's on the inputs. All I can do is monitor the outputs. If the output is high, it means the inputs are the same. If the output is low, it means the inputs are different. Y'all understand that? Now we can do that one. This is the same gate, by the way. They just drew it in negative. They just do it in active logic, right? You understand that? So let's go over here and do this guy. Let's see if this is different. So I'm going to come over here and erase the output. Start off with 0, 0. And what would I have right here? 0. What would I have right here? It says any high to get a low. So I don't have any high, right? You understand that? So the output would be 1. That's the same thing, isn't it? I don't want to erase all rich. Get yourself in trouble. That's what we had a while ago, wasn't it? Two lows gave me a high. Let's do this. Let's do this circuit right here. 0, 0. That would give us a what right here? Give us a 1. It says all highs to get a low. What would we get right here? It says any high to get a low. We get a 1 right there. What we get right here? What? It says any high to get a low. Do I have any high? No. This says all highs to get I'm sorry, this says all highs. This says all highs to get a low. This says any high to get a low. Right? You understand? So what would I get? I get a 0. And then I put this. Hopefully it'll go to a 1. We should get exactly the same. We should get exactly the same truth table, but it's going to be opposite. So what would we get out of this? There's no way in the world I could have all highs. I can't. Don't look at it. Yeah, but we don't have all highs, right? Okay. What do I have right here? So what would the output be? Huh? Yeah, but this is not what I'm expecting. These circuits are in the book, I think. I can't remember what it says. Figure 6.4. Let's start off again. 0, 0. This will be a 1. This will be a 1, right? Zero, 1. This will be a 1. This will be a 0. This will be a 0. Is that right, guys? Yes or no? So this would still be a 1. This would be a 0, right? This circuit ain't gonna do anything. Is this the one in the book? Are y'all in the book with me? That's nothing but an and. I expected 2 1s right here. Y'all look that over, guys, and see if I did anything wrong. So, 0 0. It says all highs to get a low. We don't have all highs, right? Y'all see the mistake I'm making? I don't think I'm making any. It looks like the circuit is wrong, don't it? Let's try this one. 0 0. What would I got here? And I'd have 0 on the bottom too, right? So that's not it either. Huh? Yeah, so that'd be a 1. What would this give me? Then 0 1. What would this give me? Let's give it a 0 right here. Yeah, I can't get these to work. So let's use these. Now I'm gonna use these. These are not in your books, but this is gonna. Let's do the top one, and I'll figure that out later. What's going on? So 0 0. What would I have out of this? Everybody agree with that? Yeah, we're going to work out the whole thing. We're going all the way. So this is a circuit, right? So what we're trying to do is figure out what we get out over here when I put that over there. So I'm waiting. What do you think, Barry? Would not be right here. I don't know. Y'all doing it. 0 0 0 1. Let's see. So what would I get right here? Okay. What would I get right here? What would I get right here? What would I get right here? Any high to get a low. Do I have any high? Are we okay, guys? The normal tendency for people, they see that little bubble, they want to put a 0 right there. I mean, I don't know what it is, but that's just something they do instead of trying to figure out what the gate is. So we're doing a B on the bottom. Something gonna happen here, guys. I want to know what's gonna go on here. Yeah, that's where we're going. This is a circuit. We got 2 input circuit, right? We got 4 inputs on the circuit. And what I want y'all to do is tell me what I'm going to get over here on the output with those inputs. Not what I get right there. I want y'all to tell me what the whole circuit is. Okay, let's see. So out here I get a what? I get a 1. I got a 1 and a 1 right there. I get a 1, right? You understand? I got a 0 right there. Do I have any high? Any high is going to give me a what? Low. I think this in the test. All we're doing is just tracing 1s and 0s through a circuit. So what's my next combination? This right here. It says embarrassing? Yeah. Go ahead, Barry. Okay, so let's go back. Okay, so I put a what right here, I put a 0 right there, and I put a 1 right there. Okay, so that 1's going to come right there. Okay, so there's a 1. Do I have, it takes all highs to get a low. Do I have all highs? Okay, so the output would be high. So I bring this down here, what do I have right there? Okay, this guy right here takes all highs to get a high. Do I have all highs? Okay. Up here, this takes all highs to get a high. Do I have all highs? Okay, all right. This says it takes any high to get a low. Do I have any high? Okay, so that's where that 0 comes. Okay, you okay? Yeah, I thought Mark said this was embarrassing. I was saying, yeah, it is. Okay, guys, what would I have out? Good job. Y'all understand why? Yes or no? Yes, huh? Well, no, let's go through one at a time. What would I have right here? This says what? This says what? All highs equal to what? Low. Do I have all highs? Okay, so the output will be high. Okay, this gate right here says all highs equal to high. Do I have all highs? Okay. So what do I have out? I'm not even going to look at the next one. I'm through. Because as soon as I got that right there, I know the output's going to be what? It's going to be 0, right? You understand that? I mean, we can follow the other one through if y'all want to. So this will be a 0, this will be a 1, this will be a 0, that was a 0, 1. Yeah, but as soon as you get any on an OR gate, as soon as you meet that any, you don't have to worry about the rest of them. Y'all understand that? Okay. So last combination. God, I hope not. So I got a 1 and I got a 1, right? So what does that give us right here? Alright, what does it give us right here? What does it give us right here? Okay, do I have any high? So if I look at this output, if I get a 1, what does it tell me about the inputs? They're the same, good. If I get a 0, it tells me they're what? Different. Okay guys, y'all do this one. Anybody got the first one? Here I'm using a NOR. Here I'm using a NOR. So Mr. Thomas Hickenbotham said that's what we would have there. Do y'all agree? It's not inverted. Up here it is. Down here it's not. So what can I tell about the bottom one? If I see zeros on the output of this one, what does that tell me? It tells me the inputs are the same. If I see ones, it tells me they're what? They're different. I don't even have to know what the inputs are. So what I'm doing is I'm comparing two binary digits. Not numbers, binary digits. But we can definitely take this over and add them up. Okay. Everybody okay? Okay. So it starts out looking like a NOR gate. Right? You understand? Starts out looking like a NOR gate. But if it was a NOR gate, this right here would be 0 also. Okay, you understand? Yes or no? So the function of this is what we call an exclusive NOR. This function down here, we call it an exclusive OR. Starts out looking like an OR gate. The only difference is this 1-1 combination. The 1-1 combination is opposite. So the 1-1 combination up here is opposite of a regular OR. The 1-1 combination right here is opposite of a regular OR, right? You understand? We use this function all the time. Can't you imagine having the ability to compare binary numbers to see if they're the same? I worked on a post mill machine at Beach's Machinery up in Fairfield. And the operator would come in and he had thumb wheel switches. He had flip around. And what they were hexadecimals. They were BCD switches. And then the thing would start moving. And so he'd hit a button and he put X and Y in there where he wanted that mill machine to go. All he did was just punch in numbers. And he hit go. And then while it was going, it had little sensors on there that pulsed every, I think it was for like maybe not even a millimeter. I don't remember what it was. And this went into counters, and the counters would go in. So the thumb wheel switches came into one side of the comparator. The counters from the position came into the other. When they matched, the thing would stop. Well, what did they put in there? Well, they put down comparators. That's all it was, just a comparator. In fact, the comparator that we was going to use, that we'll use, was in that system. Very, very simple process, but we have to have the ability to compare these. We use these so often that they have their own symbols. So we start off with the basic symbol of a NOR, but then we put a ghost on the end, put it like that. So this would be what we call this is the symbol for an exclusive NOR. And this is the symbol of an exclusive OR. Contrary to OR gates and NOR gates, exclusive ORs and exclusive NORs will always have two inputs. No more, no less. There is no such thing as a 3-input exclusive OR gate or an exclusive OR. Two inputs. Because that's what they're doing. They're comparing two binary numbers. That's all they're doing. If both inputs are the same, and what you look at and what you got to understand is the symbol is telling you what you get when they are not equal. So that top one, notice, it's got a bubble on the output. But if we look over at the truth table, if they're not equal, I get a 0. So the bubble on the exclusive gates is telling you what you get if the two inputs are not equal. Right? You understand? So this tells me I get a high if they're not equal, so I get a low if they are equal. And that confuses people sometimes. Because they see that bubble out there and they think, okay, when they're equal, it's going to give me a 0, right? You understand? Or they don't see the bubble. They say if it's equal, it's going to give me a 1. Well, what these gates are telling you is they're telling you what you get if the inputs are not equal. Everybody okay? So if both inputs are the same, the output will be low. If both inputs are different, if the inputs are different, the output will be what? High. And there's the Boolean equation for an exclusive OR gate. So it says if they are not equal, so here says, so the output is high, right? It don't have a bar above it. It says the output of high is A is low and B is high, or if A is high and B is low, the output will be high. So this is saying if they're what? If they're not equal. Everybody understand that? Yeah or no? This is a digital comparator. So we can compare numbers. If I wanted to see if let's say if I wanted to say a 2-bit number was, two 2-bit numbers were the same. Right? You understand that? Or let's say I wanted to do 4-bit numbers. Well, how could I do that? Well, I could come over here and use 2 exclusive ORs. And this could be A1, this could be B1, and this could be A2, B2. I need more, don't I? I don't have them lined up good, guys, but and this right here, and then this would be what? This would be A3, this would be A0, this right. This would be A0, B0. So I'd be comparing this one with this one, right? I don't know why I did that. So here's A. Here's the A number. Here's the B number. Okay. Then down here I would compare. This would be 1, 2, 3. So this would be A1 and B1. And this would be A2 and B2. This would be A3 and B3. So this guy here, if they're the same, if the inputs are different, if the inputs are the same, the output would be what? Low, right? You don't understand that. This guy right here is looking for all lows to get a high. So if the inputs were the same, if these two numbers, if number A and number B was the same, the output would be a what? Would be a 1. If the two inputs are not the same, the output would be a what? Would be a 0. So all you can do is take the outputs of these. If it was an exclusive NOR, I would use a regular AND gate. Here we're using an OR gate, right? Or negative AND. So we could very easily come up with a comparator. That comparator compares just about any number of bits that we wanted to compare, any size number. So here's timing diagrams. Y'all know this is going to come through. So what does this say? This tells us that the inputs are not equal, right? I understand that. Okay. So here, this is the low or this is the low. Are the inputs equal? Okay, so what would this one give us? It would give us a high, right? You'll understand. And then what would this one give us? Give us a low. Right? You'll understand. Here, huh? Well, they are, because you see this, anytime you see that bubble, it means the opposite of. So whatever this one gives us, this one is always going to give us the what? Opposite of. Or whatever this one gives us, this one's always going to be the opposite of because of the bubble. And that's all I did back here to go from an exclusive OR to an exclusive NOR to an exclusive OR, is this right here uses the what? This uses an OR, this right here uses an OR. Because I wanted the what? I wanted the opposite of. So we could have came over here and very easily, that's what I can't understand. So some of these are not right. All I had to do was change this from a NAND to an AND, and I would have an exclusive OR, right? You understand that? So, but these over here are not right. What I did here is I literally went into a comparator that you can buy, 7485, and this is the exclusive ORs that they use. They're nothing but a. But notice this took what? 1, 2, 3, 4 gates to get this, but we represent this with a symbol. So we call this an exclusive OR, an exclusive NOR gate. That's what we call them, but they're not gate. They're combinational logic. It's just that these guys have been around so long, and you can understand they compare. And I want to compare things all the time, right? You even do that you do it all the time, right? You understand that you compare two things. Normally, but these guys here can only compare 2 things at a time. But then we can group them together to compare more than that, right? More than 2 digits. But these guys have been around so long that they have their own symbol. So all your other combinational logic is going to be rectangles. You gotta look at the pins and see what the pins are to determine what type of combinational logic circuit it is. The exclusive OR has their own symbol because that when we get into counters and multiplexers and flip flops and latches, those are all going to be always going to be rectangles. And that's where it becomes very important for you to identify the pins. Yeah, so I don't know why they did that, because it would have been very simple to go between the two. Everybody okay on the Boolean equation? I need to write that down. It's in the textbook. So this is a symbol you're going to have to learn. It's not in your basic gate symbol, but it's a symbol you need to learn, right? Learning the symbols of your trade is your trade. If you don't know the symbols of your trade, then you're not going to be in that trade very long. There used to be a comedian, I hadn't seen him in a long time, his name was Stephen Wright. You ever see Stephen Wright? He was so funny. And he had that real dry sense of humor. He threw jokes out like, somebody broke into my house and stole all my furniture and replaced them with exact replicas. But he says, I have a map on my wall of the United States, and down in the corner it's got the scale, and it says 1 mile equals 1 mile. So. He said, I got a switch on my wall. Every once in a while I go over and flip it, and I couldn't tell what it was doing. He says, the other day I got a phone call from a lady in Germany that said, cut that out. Yeah. You get that, right? You don't get that? So he was flipping a wall over here, and he was flipping a wall over in the United States, and it was flipping something over in Germany, is what it's. So understanding this, if it's, you know, could you imagine being a carpenter going out there and they don't have symbols to build a house, and you can't read prints? Can you imagine what type of house you would come up? Or a plumber didn't know what, huh? You come up with them houses where they're built upside down, right? These are the truth tables. We've already, so this is the truth table for an OR. No, it's not for an OR. The equation for an OR, so X would be equal to A or B. That's the equation for an OR. This is the equation for an exclusive OR. Now, shorthand, what we do, we don't put E down, but shorthand, they abbreviate the exclusive with an X, and they'll call it that. So you ever see that, X OR, that means they're talking about exclusive OR. That's what we use to abbreviate this. So we have XORs and we have XNORs. They always have two inputs, but they'll take two parts of your equation. Okay, you understand that, because it's looking at, and what it's going to show you, it's going to show you what's going to happen if they're not equal, right? You understand that? So when you said OR, I guess you made it exclusive. So this is the truth table for an exclusive OR. And it's got the name exclusive because the double ones are going to be different. An exclusive NOR. So exclusive NOR, we get a 1 if they are the same. So an exclusive OR, it says X is equal to A, B, or AB. And we did this, right? You understand that? Because this is telling us what we get. We need to get a high. On exclusive OR, you get a high exclusive NOR, you get a high when they're equal. In exclusive OR, you get a high if they're not equal. Okay, y'all understand? So here it says if both A and B are high, or if what? Not A, not B, or A and B is low, we'll get a high out. So this is the equation for a exclusive NOR. So there's only one equation. So every time we come up here and solve for a equation, we're trying to solve for what we get to get a high. So when I come over here, let's say I have this symbol right here. Well, what we do is we come over here and we say X, or we'll come over here and we say what? We'd say A and B would give me a high, and then this tells us to invert the answer. That's what it tells us to do. So this says, okay, it takes this to get a high, and this tells us to do what with that, to invert the answer. So that's why these equations are a little different. And by the way, in motor controls, how would you do this? Well, you do this. So an exclusive OR would be like this. Any of y'all taking PLCs? And what does this tell me? So if I put AB, then up here I'd make this, and down here this is AB. Oops, sorry, AB. Down here I would do that. That would be that equation right there, right? You understand that? Okay. Over here, what would I do? Well, here if I call this AB, and down here I call this AB, And up here it says I'm going to make these normally open. Down here I'm going to make these what? Normally closed. And that's the way you figure that out. That's how you would do exclusive ORs and exclusive NORs with the relay logic. If you're in PLCs or motor controls, we're going to take motor controls next. We'll look at exclusive ORs, ANDs, NANDs, and ORs done with relays. We can do that. Huh? Week after next, right? No, next week, you're right. Next Tuesday. Not over here, over in A building. All the motor controls are over there in A building. We just got a bunch of we got other symbols. In PLCs, when you draw diagrams, and unfortunately they don't teach that a lot. In PLCs, everything, you got contacts. You either got a normally closed contact or a normally open contact. Well, in motor controls, we got contacts that are controlled by relays, then we got push buttons. Well, push buttons has a symbol. So a normally open push button would be this. Now, if you got into how you wire the PLC up, how you wire the input ports up on a PLC, they use the symbols used in motor controls for push buttons and stuff like that. But unfortunately, in intro, we don't have that. So in motor controls, you'll learn the symbols for the device, the input devices, right? You'll understand that. In PLCs, you still learn the logic. But it don't make any difference which one you do first. People ask me that all the time. If you take motor controls first, it makes PLCs easier. If you take PLCs first, it takes motor controls easier. So it really don't make any difference which one you take first. It'll make the other class easier. But there's quite a bit of difference. Especially when we start talking about logic, what logic does. But if you learn logic in PLCs and how to wire the contacts in PLCs, then we're going to wire them exactly the same way in motor control. Or if you take motor controls and you get into PLCs and you get into the contacts, they're going to be wired exactly the same that you learned in motor controls. So this is the truth table on exclusive NOR. So exclusive NOR, if the inputs are not equal, I get a 1. Exclusive OR. If the inputs are not equal, I get a 1. If these inputs are equal, I get a 0. So it's basically, are you okay? Yes or no? Okay, guys, what can we do with these things? We can generate parity. Electrical noise and transmission of binary information can cause errors. Parity can detect these type of errors. We got 2 types. What are the 2 types? Even and odd. Okay? So y'all tell me about even and odd parity. So I'm trying to send numbers. So parity usually works. We can use parity using serial, or we can use parity using parallel. Normally it's limited to 8 bits. With this bit right here usually being what? Parity bit. Of course, they eventually went to 9 bits, with the 9th bit being the parity bit. Originally, they started off with 8 bits, with the most significant bit being the parity. So tell me how parity works, guys. So when you have parity, you have equality, right? You understand? If you look that term parity up, it would say that would be equality. So that's what we're doing. We're trying to find out when something is equal to something, right? I understand. It has nothing to do with the number being even or odd. All it deals with is the number of ones in the data. So on this right here, these would be the data bits. These are the data you're trying to get from point A to point B. Then we add another bit called the parity bit, right? You understand? If I'm using 9 bits of data, then this right here would be the data, and then the 9th bit would be the parity bit. Okay, y'all understand that? Now, what do y'all want to use? Odd parity or even parity? Well, a while ago we did odd, even, so let's do odd. So I'd make up a 7-bit number. I just threw that down. And all I do is count the number of ones in my data bits. Okay, so how many do I have? 1, 2, 3, 4, 5. Is that an even number of ones or an odd number of ones? What do I want to do with the parity bit to keep them all, to keep it odd? Well, if I put a 1, that'll make even. So you count the parity bit when it checks it, right? You understand? So I've already got an odd number. I want an odd number. So what am I going to do with the parity bit? The parity bit is going to be a 0. Because we're trying to keep the total number of ones in the 8 bits always even, right? Always odd. Y'all understand that? Yes or no? Huh? Which you pick. Sometimes, in the old days it was. So what you have to understand is your transmitter and your receiver had to run the same parity. So if you transmitted even parity and your receiver received odd parity, you'd get parities all the time. You get parity errors all the time. Yeah, we have 2 ways we can handshake. We can do what we call software handshake, or we can do what we call hardware handshake. Y'all know, in computers, y'all know the difference between hardware and software. Okay, so if I do hardware handshake, what that means is I've got additional wires in my interface that handles handshake. If I do software handshake, I send codes between the 2 pieces of equipment that indicates if things are okay or not okay. Well, we'll look at the ASCII code is a perfect example. So I'm gonna come up here and I'm gonna come up here and I'm gonna now most of our devices now, except for the microprocessor, inside the microprocessor it uses hardware handshake because it's trying to send stuff around billions of bits of information per second, right? You understand that? So it's got to make sure it's got to be all synchronized. So it's got what we call a control bus, which is your handshake, and there's wires. So that's hardware handshake. The problem with hardware handshake is it costs a lot of money over distance, right? You understand that? So just about all your interfaces now are software handshake. Now, if we come over here and we look at the ASCII code, and it's down here in your powers chart, right? So this is the ASCII code. Now look at columns 1, 0, and 1. Let me turn off, I don't know why it keeps going by, guys. Let me turn off my, so I don't put on my punch face. Look at column, so 41, column 4, row 1 would be an uppercase A. What about these guys over here? Null, DLE, start of transmission, end of transmission, DC1, DC2, DC3, end of text, start of text, acknowledge, not acknowledge, sense, ring the bell, backspace. What are those? Those are handshake codes. So what we have the ability to do is I have something that I don't want my printer to print, right? You understand? Or I want to verify the information was sent. Well, I send out a number, and then I send back. Then if my receiver sends back this guy right here, which says not acknowledged, what does that tell me? Okay, so what would I do? I would resend the data. If it sent me back an acknowledged, then that means, so I send it data, it sends me back acknowledged. I send it more data, it sends me back acknowledged. So that's handshake. Okay, understand? These are not wires. These are what? These are codes. That's what they are, codes. Most of the time they use these DC codes. These are software definable, which means the software decides what the handshake codes mean. DC 1s, 2s, 3s, and 4s. Hardware handshake means I've got to put what? Got to put wires in my interface. So I'd have to have multiple wires running out there. So if I ran a clock, then if I did synchronous, that would be considered a handshake, right, to do synchronous transmission. So start of text, end of text, start of form feed. So I can tell do a form feed. I can come up here, and these are still true, by the way. So you go in there and you look at, you ever see where you like take a link and you paste it and it's got like a $20. I'm sorry, it got a %20, and those are control codes. The percent sign tells it that this is a control code, and then that 20 would be the code for a space. And if you look at your Word, you'd have a space right there. And so a space is a control code. It's not printing anything. It's just telling the hardware to move over one space. So yeah, these would all be considered what we call software handshake. Now normally USB is software handshake, serial ATA is software handshake, Ethernet is software handshake. We only got 2 wires, guys, that's used to transmit data. Which has nothing to do with exclusive ORs and exclusive NORs. But it does do parity. So the more wires I have to add between my transmitter and receiver, the more expensive the interface becomes. And so the only real advantage you get out of hardware handshake is speed. Well, if your hardware can't keep up with that anyway, right, you understand, then why use hardware handshake? Why not use software handshake and just sacrifice some time by sending these codes? So USB is totally software handshake. And like I said, they don't use parity much anymore because it took 1 parity bit for every 8 bits or every 9 bits of data. Every 9 bits of data, 1 parity bit. You wouldn't use a parity bit to represent 16 bits of data because now it becomes a lot less efficient, right? You understand that? Because you got 1 bit looking at 16 bits. So they came out with a method they call CRC, which is a code, which is really neat the way that works. So we use what we call a CRC code now. So normally when we send data, we send it in blocks now. Ethernet is 4,096 bytes per block. That's a lot of bits, ain't it? But then they attach like a 16-bit CRC code that represents all 4,096 bytes. And it's very accurate too. I mean, extremely accurate. CRC 16, which is a 16-bit code they put on the end, that's like 99.9% accurate. CRC 32 is like 99.99999% accurate, and that's usually what you use sometimes. CRC 16 is the most popular. So yeah, now it's fine. So y'all did it. Well, so I'm doing. Let's say I'm doing odd parity, and I'm sending this guy right here. So this is 8 bits. So this would be a 9-bit, including the parity bit. And I'm sending what? I'm sending odd parity. So what would the parity bit? What parity bit would I send? Okay, it'd be a 0. Why is that? got to start 1, 2. It has nothing to do with whether the number's even or odd. All you do is count the number of ones, right? You understand that? 1, 2, 3, 4, 5. It's already an odd number. My receiver picks it up. It comes up here and checks to see if it gets an odd number. If it don't get an odd number, including the parity bit, an odd number of ones, it sends back a code saying it's not, or it either sends it back on a wire if it's hardware handshake, or it sends back a not acknowledged, and now the transmitter knows to do what? Retransmit and retransmit. Yeah, I used to. When memory was new, solid state memory was new, we got parity errors quite often. Y'all have heard of the blue screen of death. We used to see that quite often. Luckily, we don't see it much anymore. So it adds a bit to the binary information to either keep it always the total number of ones what? Odd, or the total number of ones always what? Equal. Okay, guys, y'all take a break. Good thing. Oh, I got a whole page for one. What's that?
I noticed something on the calendar.
Wouldn't surprise me.
April 26th, we got test 3 for both days. We test 4 for South State and Delaware.
Gotta have it. That's
Huh?
on what?
It's on a Wednesday, but one class is Wednesday, one class
Oh,
is
okay.
Thursday.
All right. Don't surprise me. Those things don't pop up there instantly. Automatically, I have to key them all in. Questions on parity? Yes, no? Are we okay? Everybody okay? So, we're not going to go through all these circuits. Odds are you're not going to run into exclusive ORs that do parity, but exclusive ORs can do parity, right? Because they can see, well, if we got an even number of ones or an odd number of ones, that can be done pretty easily. So this is a parity bit right here. Let's see what parity it generates. So these are only 4 bits. So let's just make up something up here. Okay. So how many ones do I have? I got 2. So that's an even number. So I got an even number. So how does this work, guys? So what would I get out of here? So this shows us what we get if they're not equal. Are they not equal? Yes. Over here, they're not equal here too. So what I get? Okay, over here they are equal. So what? Now this is a NOR. So this looks like it's odd parity. Yeah, be careful there. So, huh? So let's put an odd number up here. So we'll put the number 3. What I get right here? 0. What would I get right here? So it looks like we're doing odd parity, right? So this is the parity bit. So what we would actually send, this is what we're sending. We're sending the 4-bit number. And then this bit right here, we go ahead and send it. This would be the parity bit, and that's 1. Right? You understand? So let's put an even number, let's put an odd number of ones up here and see if the parity bit goes to a 0. So what would I get right here? Get a 0, what would I get right here? 1. What would I get right here? Remember, this shows us what I get if they are not equal. So this says I get a high if they're not equal. It says I get a high if they're not equal, but they are equal, so what do I get? I get a 0. The 0 comes up here. It says I get a high if they're not equal, so I get a 1. This shows I get a low if they're not equal, so I get a 0. So what we're doing is we sent this guy right here, and then the parity bit. The parity bit went to a what? A 0. So this would be a circuit that generates odd parity. What would I do to make it generate even parity? Well, I'll change this from an exclusive NOR. I'll change it over to an exclusive OR. That's all I'd have to do. And then it would generate what? Even parity. So this guy generates odd parity. And all I'd have to do, if I wanted to add 2 more bits, then I'd just come over here and put another one of these guys, right? You understand? And this output would feed that. And now I would be able to check. We've run in 2, so now we'd be doing 6 bits. But this is going to be instantaneous. So as soon as I send these bits out, so these bits, what we would do is this is what would happen. Is we would have our parity circuit. So this would be parity. It would go out. This would come over, and it would go out. This would go out. This would go out. And this right here would go out. It would go out on the side right here. So this would go out. This circuit right here would go up here. It would instantaneously generate parity. So as soon as I sent this out, I mean, the parity would be there, right? You understand that? Now, odds are parity is used so often, then of course, what are they going to do? Well, they're going to take this circuit right here, and they're going to integrate it into a single IC called a parity generator checker. So this is a 74280. What is a 74280? So there it is. So 74 just tells us it's TTL, right? You understand? That's not true anymore. And 280, we could look up the data sheet on this thing, and it would tell us that it's a parity generator checker. Parity generator, parity checker. Because 74 has 9 inputs, we have to connect. So one, it's an 8-bit parity generator checker. So one of them on the one that's generate parity, you hook the unused input either high or low. We'll find out. And then the other one, it would receive parity, right? You understand that? And this guy here on the fly generates parity. So here's that input 8, right there. And then this guy over here automatically generates what? It checks parity. It's got 2 outputs. It's got what output? It's got one called what? E. What do you think that stands for? Even. And what does this guy right here check? Odd. And this is on the fly. This is instantaneous. So we add another IC, and now we got the ability to find 95% of our errors, just like that. It's very unusual for EMI, electromagnetic interference, to cause 2 bits to change. It happens occasionally, but only could 5% of the time. So parity is not perfect, but it's better than nothing. Right? You understand? So it's not perfect. CRC is not perfect, but it's really, really good. Still have problems every once in a while. You ever had a problem where your computer jumps up and starts running check disk when you boot it? That's what it's trying to do. Go out there and compare the error codes and everything because something didn't quite work out when it checked out there. The ROMs in the in your computer uses something called a checksum, which is really neat. So what they do is they take all the contents of the ROM, they add them together and store the sum in the ROM. And then when every time you boot and it goes through its power on self-test, it runs through there and adds all the ROMs together. And if the two match, it says the ROMs are okay. If it's not, then it'll pop up and say you got bad ROMs. We don't see that much anymore, thank goodness. So this is a comparator. So 74LS280 or 74RET280, that would be a parity generator checker. Parallel parity generator checker. But we could do this inside, right, and then use the output and convert that to serial. We'll learn a chip later on called a shift register that we can take parallel and convert it to serial real easy. So this is the same basic circuit that I showed y'all. So we're bringing a 4-bit number in here, they're calling A. We're bringing another 4-bit number over here, they're calling B. And this guy right here, and this is the AND. So this gives us a 0 if they're not equal, right? You understand? So if this 4-bit number equals this 4-bit number, then this right here would go to a 1, right? You understand? If they're not equal, they would go to a what? 0. This is what's things neat? One thing's neat about these things is, let me go back to my blank sheet. Now, this is an exclusive OR, and I'm controlling one of the inputs. Okay, so this means if they're not equal, we're going to get a 1. If they are equal, we're going to get a 0, right? You follow this? So let's say I put a 1 over here. What am I going to get out? Okay, so I get a 0 out, right? You understand? Let's say I put a 0 in. I get a 1 out. So what did it do? It inverted. You see that? Let's say I put a 0 in there. Well, if the input was a 1, they would be not equal, so the output would go to a 1. If the input was a 0, they would be equal, and the output would go to a 0. So that means if I put a 1 right there, it acts like, the other input acts like an inverter. If I put a 0 there, it acts like what we call a buffer. By the way, there is a gate that we don't talk about. It's called this guy right here. So what's this a symbol for? An inverter, right? The circuit's called an inverter. What's that a symbol for? It's not a basic gauge, but we use these all the time. We refer to these as buffers. And we'll look at later on why we need buffers. These are the pretty common. So we got like a 7805. It's not an inverter. You look that sucker up, it's not an inverter, it's a buffer. Well, why do we need them? Well, we'll find out later on. So if we put a 0 right here, it acts like a buffer. It acts like this guy. If I put a 1 right there, it acts like an inverter. So they call these programmable inverters is what they call them. So you control, but this is all you're doing. In the old days, when video was young, y'all understand things have to be synchronized, right? You understand that? So how in the world can we send TV pictures over there? So they're sending these individual pictures. How in the world can your TV be synchronized with the pictures it's receiving? Well, they send sync pulses. We have what we call a horizontal and vertical sync pulse. Every time the camera finishes a scan, every time it finishes one line, it sends a horizontal pulse. Every time it sends a picture, it sends a vertical pulse. So your TV is totally synchronized with the images being sent, right? You understand? The old days of 8mm movies, you had to control the speed of your motor. I don't know if y'all remember those or not. Your pictures would be rolling all over the place, and you see people that just turn the dial until they got their camera synchronized to the shutter on the camper at the same speed as the TV. We can't do that. Old TVs, you had what we call horizontal and vertical holes on there that you could do things with. Now we don't worry about it because TVs have been around so long. Everything's synchronized. The old video cards, though, some of the monitors use negative sync pulses and positive sync pulses. So the video cards had a little switch on there that you could flip depending on what type of monitor you hooked up to your computer. So if you hooked it up and it was all over the place, the pictures were rolling and all kind of stuff, it means they wasn't synchronized. Then you just go to your video card and do what? Just flip that little switch. So these things are called programmable inverters, but all they are is an inverter, and you have one pin that you can make them either do what? Invert or not invert. If they don't invert, we call it a what? A buffer. And we'll pick up that term later on. And there is a need for that. It's just like in controls or PLCs, we got one contact. What kind of logic does one contact by itself? No logic. It acts like a buffer. That's what it does. So if we need a normally open contact by itself in PLCs, then we need something that don't give us don't give us or, it just acts like a go-between or a buffer, right? And that's what they're talking about here. So these would be what they call a controlled inverter. So what we're doing is we're controlling the whole thing with that one input right there. If I put a 1 right there, all these act like inverters. If I put a 0 right there, they all act like buffers. Are we okay? This is a crummy picture. Is this the one they use in your book at 7485? I've never seen this before. I think this is National Semiconductor's layout of a 7485. So find this in your book. So we're dealing with a 7485. It's a 4-bit comparator. It's a magnitude comparator. Yeah. Don't tell me they don't talk about this. If they don't, we are, because we got a lab on it. So it's got the 74LS280, and then it's got the controlled inverter. So y'all logged into Blackboard? Y'all are, go ahead and log into Blackboard.
page?
7485. Pick that other number in there, it means a lot. 74185 is like an adder or something like that. And we're going to go to our data sheets and we're looking up 7485. $74.85. So what is the $74.85? Of course, the data sheet we have is for a 74L LS85. Of course, we know what's these center letters telling us? Speed and power. Oh, there we go. The PowerPoint got, I forgot what it got, P's and Q's and all kind of stuff. This is the basic layout of, so this is our binary numbers. So these are the numbers I want to compare. One number we're going to call A. The other number we're going to call B. Y'all understand? So it's 4 bits, so there's A0, B0. There's A1 and B1. There's A2 and B2. There's A3 and B3. So B would be one 4-bit number. A would be the other 4-bit number. And what we're doing is we're comparing these two 4-bit numbers. Are you okay? Now look what outputs we have. So if this right here is true, what does that tell me? Can y'all see where I'm at? Right here. We got 3 outputs of this thing. If this output is true or if it's high, it's a high active output, what does it tell me? Y'all guys don't know what that symbol right there means? So this is telling me what? A is greater than B. If this one right here is high, then that's telling me what? A is equal to B. If this one right here is high, what's it telling me? B is greater than A. Okay. So using this guy, not only can we tell if they're equal, we can also tell if they're not equal, which one's greater. What do you think these guys are used for right here? Y'all know what cascading means? Cascading means we take one and feed it into the other. So what it means is I could take two 74 180s. I can't draw. Dang it. I can't get my drawing for them. Well, let me show you. Let's see if we can find something. And 485. Come on, let me zoom, guys. Staying the same time. Can you see what they're doing here? So here they got AB, they got AB, right? You understand? And then they're letting this one, this is my least significant, I'm sorry. They're taking the output of this one and feeding it where? In the input of that one. Let's see if we can find a better picture. Oh, this is better. Can you see what they're doing? So here's A0, 1, 2, 3, 4, 5, A0, 1, 2, 3, B0, 1, 2, 3. Now they're changing the numbers up here, but they're leaving them along down there. So they're calling this A4, 5, 6, 7, B4, 5, 6, 7. They're taking the output of this one and doing what? Feeding it into that one. So what we got now is we got what? We got an 8-bit comparator. Are you leaving, Morris?
Yeah.
You know it says on the syllabus that if you leave class early, you need to let me know, right? It's on the syllabus that if you leave class early, you're supposed to let me know. You know that, right? No, I did not say that. I'll show you the syllabus that we went over in class. You want me to show you that? Where it says you need to inform the instructor if you leave class early or if you come to class late, you need to inform the instructor. Okay. And we went over that in detail at the start of the class. I don't know how it could have been a misunderstanding. I'm the one that makes the rules for the class. Barry don't make the rules for the class. I make the rules for the class. So, you know, you need to let people know when you leave or come in. If you left work early, would you just leave work early? Not tell anybody? Oh, okay, then. Not, yeah, it was. Huh? What's that? I thought when he said, I thought he told you that, huh? I thought you pointed to Barry and said, he said we just leave. Well, when you said he, who was you talking about?
I was talking about you. When we first started taking this class, I don't wear the bear thing in my pocket that you said you don't have to ask to leave if you grown, just get up and leave. That's what I thought you said. I could.
I don't know if you could be wrong. Let me show you the syllabus. We read the syllabus. We read the syllabus in class.
It was, I believe.
So here's the syllabus for this class. And we went over the syllabus in this class. And I think it was in the syllabus quiz too about leaving the class early. I think that was in the syllabus quiz too. My computer won't load. I'll show it to you next. Or you can go and look. You can go and look for it on Blackboard. You got to understand there's a safety situation going on here. That if you leave and I don't know you leave, right? And they have an evacuation in the college. We go outside and you're not here. Then somebody's going to have to come back in this building. Right, you understand that? And that's exactly what I said during at the start of class. But go and look. Go listen to the first lecture, first class lecture.
Yes.
I wish I had a. Well, I guess I could just say. Think about it. And if you don't let me know when you come here, I call roll at the start of class, and I told y'all at the first of class. After that, I'm through with roll. So it means if I mark you absent and you don't let me know you're here, then by George, you're what? You're absent. And I think I told you about Ron Moon. He was the dean of instruction here at the college. He became interim president after we'd gone. You know what he told us to do? He told us to lock the door at the class start time. That's what he told us to do. He said if people can't get to class on time, they don't need to come to class. That's what he told us to do, which makes sense. I never did. So if y'all leave early or you come in late, you need to do what? Let me know. Just get up and walk. Does anybody else in the class remember me saying that? Just get up and leave when you need to leave. I'll go back and play that for you. I thought we, huh? No, play it.
No. No, I'm gonna do that. I'm gonna put it quick. For every class.
That's on the syllabus quiz too.
It is.
This is the truth table, by the way. This is what I wanted to show y'all. Is where they've actually taken 4. So each one of them does 4. So 1, 2, 3, 4, 5. So that's 20 bits. Here's A's and B's, A's and B's, A's and B's, A's and B's. So there's two 20-bit numbers. They're taking the output of each one of these and feeding it into the A and B, A and B, A and B inputs of this one over here. But they're checking to see if two 20-bit numbers are the same. And not only can we know if they're the same, we know if they're different, we know which one's greater, right? 7485 is when I worked on that machine at Beach's Machinery, that whole logic board was nothing but bipolar transistors. And they did this, and one set went out, and I replaced that. I don't remember how many transistors. I replaced it with this guy right here. And it's probably, if they're still using that post mill machine out there, I imagine it's still got my 7485 in there. Got a bunch of transistors, and they got one IC and a socket and a wire wrap socket. I needed to show y'all that too. But one of the methods we use when we're prototyping digital logic circuits like we're doing is when you get a circuit board made, it's very, very expensive, right? You understand that. So one method we do on ICs is something referred to as wire wrap. So you can buy you can buy wire wrap sockets. And then you can buy a little tool. I'll show it, if y'all remind me next class, I'll show it to you. But you just spin it on there, it works out real well. And this is the circuit. And what's nice about this, if you make a mistake, you can always change the IC, you can put a new socket in there, you can undo the wiring and redo it real easy. And that way you can prove your circuit before you ever put into a board. The first computers I worked on, the memory cards was put out by a guy that worked for NASA, Rick Thomas. And his memory cards were wire wrapped when they first came in, because that's what we was trying to do, was trying to put it in actually a commercial application to see if it was okay before he had them made into printed circuit. Made them in his basement down in Miami, Florida. Yeah. Yes, I'll show it to you. It's called a wire wrap tool. You can still, they're still out there. They're still popular. You can't, I don't know if you can get them any place locally anymore, but you can definitely get them through eBay or Jamico or any online electronics store. It's called wire wrap. And you can see the advantage of that over getting a printed circuit board. So I guarantee you every microprocessor that was originally developed was developed just like that. And they wire wrapped it up before they started doing what? Now they don't do it much anymore because the processors are being around so long and everything's so standard now. But when they first started making microprocessors, everything was made out of this logic that we're looking at now. They wire wrapped it up and then made them do math and stuff like that. Okay, one more thing we need to look at. So we can use exclusive orders for comparators, right? Y'all understand that? Pretty neat. Okay. Yes, I wanted to add these two numbers together. How would you think I'd do this? What do you think? What's 1 plus 1? Yeah, well, so let's say I'm over here and I've got a number like, and you got to understand what you're doing in base 10, right? So if I've got 68 and I come over and add 39, what do? You add these together, okay, and that'd give me what? 7, and you carry up, well, here, base 10, you can carry up to almost up to a 9, right? You understand? Up to a 5. Base 2, the most we can carry is carry a 1. So 1 plus 1 is a 2. Well, I'm going to write down a 2, but I'm going to write it down like that. So it's 0 with a carry 1. Then I've got 1 and 1. What would that be? 0 with a carry 1. What would this be? 0 with a carry 1. What would this be? 1 with a carry 1. This would be what? Well, I get a 1. This would be what? 0 with a carry 1. 0 with a carry 1. 0 with a carry 1. 1 with a carry 1. 0 with a carry 1. And then up here I just write down 2. You just did binary math. Subtraction you borrow, and subtraction is exactly the same, but on binary you don't borrow a 10, you borrow a what? No, you borrow a 2. Yeah, you borrow a 2. So yeah, you borrow a 2. No, it's the same. We're doing the same thing. We're doing the same thing here. So here we carry on 2 on binary, on decimal we carry on 10. But when we carry on 10, we carry a 1, right? Y'all understand that? Well, here when we carry, so if I come over here and now remember down here, we've only got 2 things that's possible. That's a what? A 1 or a 0. So 1 plus 1 is what? 2. Well, if I wrote down a 2 like this, I would write it down like that. Okay, so I'm writing it down like that, but I'm going right here, and where am I putting my other one up right there? Down here, this would be a 2, right? This would be a 2. This would be a 3. Well, how would I write down a 3? I'd write down a 3 like that, but I'm going to put my 1 there and carry my 1 up there. See that? And then this right here would be a 1. This right here would be a 0 with a carry 1. Now, if we subtract, okay, what would I do here? Well, up here, if I had to subtract, you're not borrowing a 1, you're borrowing a 10. No, on base 10, let's say I was going to subtract 90 and I was going to subtract 36. Well, a lot of people come down here and make this 8 and they'll put the little 1 up there. They say they're borrowing a 1, but you're not borrowing a 1, you're borrowing a 10. Well, what would we borrow here? I'm going to borrow a 2. So I can't subtract that. I'd mark that out and I'd put a 2 up there. I borrowed a 2. No. This would give me a what? This would give me a what? This would give me a 1. Okay. Then these are 0. What would that give me? 0. I can't borrow. I'd borrow a 2. That make that a 0, makes that a 2. That'd make that 1. Let's see if that works. So I'm taking 10. This would be a decimal 10. This would be a decimal 5. What's 10 minus 5? 5. What's my answer? 5. So in decimal you borrow 10s, in binary you borrow. So every time you borrow in a base, you borrow the base. So if I was subtracting in base 16, I would borrow a what? A 16. If I'm subtracting in base 8, I would borrow an 8. If I'm subtracting in base 2, I borrow a 2, right? You understand that? And that's binary math. Well, look at this. If I got a 1 and a 1, I got a 0. If I got a 0 and a 1, I get a 1. Huh? Yeah, if I've got a 1 plus a 1, that gives me a 0. Okay.
Okay, what about a 0 and a 1? Why you get a 0?
Well, you don't.
You got 0 right there.
No, we gotta carry. You gotta keep up with your carries.
It's something.
Yeah, I see these carries up here, so I gotta carry them. Yeah.
When we did this in PLC, and I asked Mr. Claire how to do it, he had forgot. He's like, I'm gonna get that to you.
What to add? I mean, to me, it's easier to add binary. To me, it's easier to add binary than it is the decimal. I mean, good gracious. Your answer is going to be a what? A 0 or 1, right? Or when you carry a 1, you do the same thing when you exceed it. Subtracting binary to me is easier. Multiplication, you do exactly what you learned in decimal. You learn exactly what you did, but you gotta add columns. What do you mean? Not if you're doing binary math. The only reason you convert to decimal is why. If we need a way. So your computer does binary math. I mean, it does this on the fly. It's got adding circuits and dividing. It does binary, but it don't display your answers in binary because why? People don't know binary, so it converts it over to decimal. So the only reason you'd go to decimal is if you need it. If you don't need it, then so if I've got a comparator, all I want to know if they're the same or if they're different, right? You understand? I don't care. I don't want it in decimal. I just say, okay, I'm comparing A and B. Well, I would want to know if A is greater than B, if A is A less than B, or if they're equal. That's all you're looking for on a comparator. If I've got an adder inside a machine that's adding parts together, I don't care but if they wanted to display the number of parts to me, Barry, we'd have to do what? We'd have to get it to decimal. Not unless you was a binoid. I remember the old Star Trek. They had a race they called binoids, and they talked in binary. So they did little clicks. Really neat. Serial, asynchronous, by the way. So if you look at this, so when I got a 1 and a 1, I get a 0. If I've got a 0 if I got a 0 and a 1, I get a 1. If I got a 0 and a 0, I get a 0. Y'all understand what I'm saying? Yes or no? So this is the truth table for this guy right here. All I got to do is figure out how to come up and get a carry. So when do I get a carry? So this guy right here so if I come up here, if I come up here and put this, I'd get a what? I'm sorry. If I come up and did that, sorry, let me redo this. So if they're not equal, I get a 1. So I'm going to add these two together. So what's 0 plus 0? 0, right? You understand? So I get a 0 out of this. If I come over here and added this plus this, what would I get? Okay, if I come over and put it on that, they're not equal, I would get a 1. If I came over here and put this, if I added that, that would be this and this, I'd get a 1, right? You understand? If I came up and put this, I would get a 0. If I come over here and put an AND gate out here on the side, and I call this my carry, then this guy here does math. It'll do 2-bit math. It's called a half adder. Half adder. Yeah, because it don't pick up a carry from the previous bit. So these are two circuits. This right here is what we call a half adder. This right here is what we call a full adder. So notice what the full adder does. it picks up the carrier from the, it picks up the carrier from the previous bit. See that? And then it generates a carry to the next bit. So this guy right here, I could come up here and I could combine these circuits, and we got a circuit that does math, adds. By the way, computers can't subtract. You don't know that? Calculators can't subtract either. They subtract by addition. We'll look at that later on. By adding and negative. That's the way they subtract. It uses something called two's complement, which we might have time to get into or not. But we've got a circuit. These exclusive ORs, they can do what? They can add. They can do math. Well, they got a whole chapter on the next chapter we're going to skip over is on binary math. We just get just a little glimpse of it. So what can the exclusive ORs do? They can compare. What else could they do? They can what? They can add. You can't say they do math. They can add. They can't subtract, but we can compensate for that real easy. We can subtract by addition. So just to give y'all, let's say I take a number. What's that equal to? This is equal to 10. Okay. And let's say I want to come up and I want to subtract 5. Okay, so what would I do? I would come up here and can't subtract this. I would borrow, and what I would borrow? 2. Okay. Then this would equal what? 0. I can't subtract from that, so here I'd make that a 0. I'll borrow you 2 and make that a 1. Now, I'll put another 0 out here for an obvious reason in a minute. Let's say I come over here and do this. No, I'm sorry, wrong one. The other one worked okay. Let's say I come over here and do this. Now what I'm going to do is I'm going to add and I'm going to drop the carry over here. So what do I get here? What do I get here? 0 with a carry 1. What do I get here? What do I get right here? And I drop my carry. I added those two numbers and I came up with the same answer. So this is the way we represent a positive 5. This is the way we would represent a negative. We call it two's complement. You see I did that in my head, right? Two's complement was a method where we invert the number. So I come over here, so I've got a 5. I invert the number, so what would I come up and get? Come up and get that. And they call it two's complement because you add 1 to this, and you come up and get that, and that's the way you represent the negative number. Now somebody told me a trick, which is really neat. They told me you invert everything after the first one. So I'd come over and do this. So there's my, this is, I'm sorry, let's come over and so let's say I wanted to get the negative for this. So I'd start off writing, I hit the 1, and then I invert everything after the first one. And that would be the negative representation of that number. I call that two's complement. So you got two's complement, you can do it 2 different ways. You can take the 1's complement, which is inverting, right? And then add 1 to it. Or you can start from the right and work to the left and invert everything to the first one. All your negative numbers, by the way, are going to have the most significant bit set, all your positive numbers are gonna have the most significant bit, 0. So if you got a calculator, and Windows calculator won't do it anymore. Anybody got their calculator? That does binary conversion. Yours does conversion.